We are looking today at BitNet, an approach to run LLM crazy efficiently, like even on a single CPU. So it does this by changing the weights and the math inside the network. So let's first understand what weights and embeddings are inside a model. So embeddings are the numbers that represent the words or any symbol that helps the model understand their meaning or any context about the word that is given, while weight decide how these word representation uh, influence each other so that the model can predict what token should come next. With every layer, weights just keep adjusting the embeddings, making their relationship clearer and more accurate. Let's go through with an example. So consider this apple. So the model turns it into numbers like that means fruit, food, or edible. So the model sees it as closer to meanings like fruit and food, not just any other random things. So weights then decide how apple relates to other words, like linking it to more strongly to eat rather than to drive. So it helps the model predict the next word correctly. So that is the role of the weights inside the model. So, but in traditional model, these weights are stored as precise numbers. Like if you can see here, uh, if it can be of any numbers that like 3.14 and 159. So, and it requires a lot of computer memory and also complex math operation to process because it uses multiplication. So that makes them resource heavy, slow, and dependent on the powerful GPUs. BitNet uses 1.5 bit weights, so where they are like only -1 0 or +1, because weights are only -1 0 or 1. The model mostly uses addition or subtraction instead of heavy multiplication that was in traditional transformer models, that was making computation much cheaper here. So that is, so this technique is called quantization, where BitNet trains model from scratch, and these low precision weights, unlike other method that compresses after training, like if we compress the transformer model, that can reduce the accuracy also. But with this quantization, that means the AbsMean quantization, where each weights decide the direction, like +1 for positive, -1 for negative, and 0 for no influence. So at every layer, the model applies these weights to the previous layer output x. So the previous layer is represented by the x, and it scales the result using one average value and then passes it forwards. So in the end, you get the same output, but the compute cost drops a lot because of the reduce in the weight size, and the multiplication is replaced by the addition. So there is no need of GPUs to do the computation. So it can run on a single CPU also. So in some cases, it's a 3.2 billion model have beaten the Llama 3 billion model also. So it seems to be ideal for medium-sized model, as a small model already work well with traditional approaches. But the only thing is it needs time for training. Currently, it is not widely adopted to the training complexity and the lack of mature tooling and compared to traditional transformer models. But it is useful for future solution, especially where compute and power are limited. So this approach can help in running large language models on mobile devices.